What came before everything? Before the stars? Before the planets? Before even the concept of time itself? Let's imagine a moment when there was nothing. Not darkness, for darkness implies the absence of light, and not silence, because silence exists only in contrast to sound. No, this was a state beyond all that, a void so complete that even the word nothing seems too full. But what does nothing truly mean? What exists in the absence of space, time, and matter? Could it be that, within this enigmatic emptiness, lay the seed of everything we know? The physicists have a name for this state: a quantum vacuum. It's not like a vacuum in space, the kind you might imagine as the void between stars. It's something far stranger and more profound. The quantum vacuum is an empty state, stripped of particles and fields, a realm where not even a whisper of existence resides. And yet, paradoxically, it is brimming with potential, a deep reservoir of possibilities, like a blank canvas waiting for the first stroke of a painter's brush. Within this vast emptiness, something was stirring. Perhaps it was a restlessness that defied the very concept of stillness, a hidden movement in the silence before existence, a whisper in the void, a flicker of something not yet realized, a spark of something that could be. But what could emerge from such a place where there is nothing to emerge from? Could it be that this nothing was not as empty as it seemed? What if this nothingness was filled with creation itself, a quiet prelude to the greatest symphony ever composed? What if, from this void, there arose a mysterious spark, a spark that would light the fire of the cosmos and bring forth all that ever was and all that ever will be? To find the answer, we must journey far deeper into the silence, into the very heart of the void itself. From a classical physics standpoint, the universe's existence poses a paradox. How could something come from nothing? The laws of physics, as understood for centuries, were governed by principles of cause and effect, actions and reactions, matter and energy. To suggest that a universe could spring forth from nothing seemed almost like proposing magic. Yet, it is precisely this question that classical physics grappled with as thinkers, and scientists began to contemplate the origins of everything we see around us. For much of human history, the question of the universe's birth was firmly within the realm of philosophy and theology. Classical physics, which emerged in the 17th century with figures like Isaac Newton, began to provide a framework to describe the universe as it was, its motions, its mechanics, and the forces that held it together. Newtonian physics told us that every particle in the universe exerts a force on every other particle. The sun's gravity holds the planets in their orbits, while the Earth's pull keeps us grounded. Yet these laws assumed a universe already in motion, filled with stars, planets, and the very fabric of space itself. The laws were silent, though, on the critical point of how all this matter and energy came into being in the first place. But as physics developed, questions about the origin of the universe persisted, even if the field seemed ill-equipped to answer them. According to classical physics, for something to happen, there must be a cause, a preceding event. Every action has a reaction. Every force has its counterpart. If the universe began to exist at some point, then what caused it to exist? And more puzzlingly, Where did the matter and energy required to create this universe come from? This was where classical physics found itself on shaky ground. Matter and energy, according to the laws, could neither be created nor destroyed, they could only change forms. In a sense, classical physics seemed to deny the possibility of a universe emerging from true nothingness. The conservation laws that governed the behavior of everything in the universe implied a kind of eternal existence, a universe without beginning or end, always in some form or another. This was comforting to some, but it did not answer the deeper existential question. As the 19th century rolled around, the picture of the universe began to change, and classical physics faced new challenges. Thermodynamics emerged, and with it, the concept of entropy, a measure of disorder in a system. Entropy brought with it the understanding that while energy might not be created or destroyed, its availability to do work was always decreasing. This led to the idea of the heat death of the universe, a theoretical point far in the future when all usable energy would be expended and the universe would reach a state of maximum entropy. This vision of the end, however, did not square with the static, eternal universe of Newtonian thought. The universe, it seemed, was heading somewhere, but the starting point was still shrouded in mystery. In this context that some physicists began to reconsider the nature of the universe's beginnings. If the universe was not eternal, if it was moving toward an end, then perhaps it had a beginning. But to posit a beginning was to confront the problem of how something could come from nothing. To solve this riddle, some turned to the idea of a cosmic egg, a primordial state containing all the matter and energy of the universe, compressed into a single point. This was not quite nothing, but it was a step toward understanding how the universe could have a finite beginning. If all matter and energy were once contained in an infinitesimally small point, perhaps it was not so impossible that this point could somehow come into being from an unimaginable nothingness. Here, classical physics found itself at a crossroads. On one hand, the laws of motion and thermodynamics pointed to an orderly, deterministic universe where every effect had a cause. On the other hand, the existence of the universe seemed to defy these very laws, as if the universe itself were the grandest of exceptions. And so, while classical physics provided no final answer to how the universe could emerge from nothing, it laid the groundwork for further inquiry. It set the stage for the 20th century, when a new theory, one that could better handle the complexities of the cosmos, would emerge to continue the search for the origin of all things. As science progressed, the answer, as it turned out, lay not in the realm of the large and the predictable, but in the bizarre and counterintuitive domain of the very small. It was in the depths of quantum physics, a new frontier where particles could exist in states of uncertainty, and where nothing could, quite astonishingly, give rise to something that the story of the universe's birth would begin to be rewritten. Before the Big Bang, before the cosmos burst into being with a flash of unimaginable energy, there was, in classical terms, we might call it nothing. But quantum physics offers a different, more nuanced story, a story where nothing is far from empty or inert. In the quantum realm, nothing is a vibrant, dynamic cauldron, a seething sea of potential that defies all conventional notions of existence and non-existence. Here, in this quantum void, we find the birthplace of everything, the stage upon which the universe itself would come into being. This quantum void, unlike a classical empty space that contains absolutely nothing, is anything but empty. Physicists like Paul Dirac and Richard Feynman, through their pioneering work in quantum electrodynamics, revealed a startling truth. Even in a perfect vacuum, where we might expect utter emptiness, there exists a buzzing activity, constant flicker of virtual particles popping in and out of existence. These particles, which appear without cause and vanish without a trace, do so in a dance dictated by the strange rules of the quantum world. The quantum vacuum, therefore, is not nothing in the strict sense. It is a restless ocean of activity, an ever-present hum of potential. Quantum electrodynamics takes us deep into the subatomic world, where the familiar rules of classical physics give way to the strange and often counterintuitive behaviors of particles at quantum scales. At its heart, quantum electrodynamics reveals that even the void, what we might ordinarily think of as empty space, is far from empty. Instead, it is filled with potential, with particles and antiparticles constantly coming into and out of existence, and with interactions governed by the exchange of photons, the fundamental particles of light. Quantum electrodynamics was developed in the mid-20th century, largely through the groundbreaking work of physicists such as Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. Their work built upon the earlier ideas of Paul Dirac, who in the 1920s combined quantum mechanics with special relativity to formulate the Dirac equation, which described the behavior of electrons. The Dirac equation revealed a surprising truth. In addition to electrons, there should exist their counterparts, positrons or anti-electrons. This was one of the first hints that the vacuum, or empty space, was more than a simple void. Quantum electrodynamics describes the interaction of charged particles, such as electrons and positrons, with the electromagnetic field. In this theory, the forces between charged particles are mediated by the exchange of photons, the quanta of the electromagnetic field. Photons, unlike electrons, are massless and travel at the speed of light. The concept of exchange here is crucial. Unlike in classical physics, where forces are seen as continuous fields, in quantum electrodynamics, forces arise from discrete packets of energy, the photons, being swapped back and forth between particles. Imagine two electrons repelling each other. In the quantum world, this repulsion is the result of countless photons being exchanged between them in an almost instantaneous game of catch. These photons are not real, detectable photons, but virtual ones, entities that exist only fleetingly, obeying the rules of quantum mechanics. This is where quantum electrodynamics begins to reveal the strange nature of the quantum vacuum. According to the theory, even in what we perceive as empty space, these virtual photons, and indeed virtual particles of all kinds, are constantly being produced and annihilated. Feynman diagrams offered a way to visualize these interactions. These diagrams are not merely pictorial representations, but rather a shorthand for complex mathematical expressions that describe all possible ways that particles might interact over time. Each interaction depicted in a Feynman diagram contributes to the overall probability amplitude for a process, and these amplitudes, when squared, give us the likelihood of observing a particular outcome in an experiment. The concept of virtual particles is central to QED. Unlike real particles, virtual particles do not have to obey the usual conservation laws that govern ordinary matter. For example, they can briefly borrow energy from the vacuum as long as they return it quickly enough to not violate Heisenberg's uncertainty principle. This principle, a cornerstone of quantum mechanics, states that the more precisely one knows a particle's position, the less precisely one can know its momentum, and vice versa. Similarly, it allows for short-lived violations of energy conservation. A virtual particle can pop into existence, provided it vanishes quickly enough that this temporary energy debt cannot be detected. Thus, the quantum vacuum is a bubbling cauldron where particles appear and disappear in accordance with these rules, creating a state that is far from empty or quiet. One of the most fascinating consequences of QED is the prediction of vacuum polarization. Imagine the vacuum as a vast sea of potential filled with virtual particles. When a real charged particle, like an electron, is placed in this vacuum, it interacts with these virtual particles. Virtual electron-positron pairs near the real electron get polarized. The positive virtual positrons are slightly attracted to the negative real electron, while the virtual electrons are slightly repelled. This creates a cloud of virtual charges around the electron, effectively screening its electric field at a distance. What this means is that, at very short distances, the strength of the electron's electric field appears greater than it does at longer distances. This effect has been measured with incredible precision, confirming the predictions of QED to an extraordinary degree of accuracy, sometimes to more than 10 decimal places. Beyond these individual particles and their fleeting interactions, QED has also led to a deeper understanding of the quantum field itself. In classical physics, a field like the electromagnetic field is continuous and smooth, stretching across all of space. What we think of as a continuous force in classical terms is, in reality, a swarm of interactions at the quantum level. And it is here, in these quantum interactions, that we see how even the void, space devoid of any real particles, can never be completely empty. This picture of the quantum vacuum as a churning sea of activity filled with virtual particles and constant fluctuations leads us directly into the concept of zero-point energy and its profound implications for the nature of reality itself. At its core, zero-point energy refers to the lowest possible energy that a quantum mechanical system can possess, even when it is at absolute zero temperature, the point at which all classical thermal motion should theoretically cease. Unlike in classical physics, where a system at absolute zero would be completely at rest, quantum mechanics tells us that there remains an irreducible minimum amount of energy. This energy, named zero-point energy, arises from the inherent uncertainties of quantum mechanics, particularly the Heisenberg uncertainty principle, which dictates that we cannot precisely know both the position and momentum of a particle simultaneously. This uncertainty enforces a sort of perpetual motion, even in a vacuum, an incessant, unavoidable flicker of energy that can never entirely be stilled. To understand this more deeply, imagine a simple pendulum. When undisturbed, a pendulum eventually comes to rest at its lowest energy state, where all kinetic motion stops. In quantum physics, however, the scenario is fundamentally different. Even in its lowest energy state, the quantum equivalent of this pendulum, the quantum harmonic oscillator, continues to exhibit tiny, jittery motions. These motions are not due to any external force or thermal energy, rather, they are a direct consequence of the quantum nature of the particles themselves. The oscillator cannot reach zero energy because such a state would require both its position and momentum to be precisely defined, violating the uncertainty principle. Thus, there is always a non-zero baseline amount of kinetic energy associated with the oscillator's quantum state. This irreducible energy is what we call zero-point energy. The concept extends beyond simple particles to the very fabric of space itself. In quantum field theory, every point in space is associated with a field, and these fields are subject to quantum fluctuations. Even in the absence of any particles or classical electromagnetic waves, the electromagnetic field, for example, is still vibrating with zero-point energy. These vibrations manifest as virtual particles that appear and disappear, fluctuating randomly in and out of existence throughout the vacuum. This is not mere theoretical speculation, but has observable consequences. One famous demonstration of zero-point energy at work is the Casimir effect. In 1948, a physicist named Hendrik Casimir, who, along with his colleague Dirk Polder, was exploring quantum phenomena at Philips Research Laboratories in the Netherlands. Casimir was intrigued by the strange predictions of quantum field theory, particularly the idea that even a perfect vacuum, emptied of all particles and stripped of all fields, still contained an irreducible minimum energy, the zero-point energy. While pondering this paradoxical notion, he stumbled upon a surprising way to prove that this energy, which seemed so elusive, could manifest itself in a tangible, measurable form. The idea that Casimir developed was elegant in its simplicity and profound in its implications. He envisioned two flat, parallel metallic plates placed in a vacuum very close to each other but not touching. According to classical physics, there should be no force between these uncharged, non-magnetic plates in a perfect vacuum. They should simply remain stationary. But quantum field theory suggested otherwise. Casimir realized that the vacuum, in its quantum description, is never truly empty. Instead, it is filled with a sea of fluctuating virtual particles and electromagnetic fields. These fluctuations give rise to zero-point energy, a sort of quantum buzz that pervades all of space. He reasoned that the space between the plates would impose constraints on the wavelengths of the virtual photons. The quantum of electromagnetic field allowed to exist between them. Only certain wavelengths would fit between the plates, much like only certain musical notes resonate inside a particular sized box. This meant that there would be fewer modes of fluctuation between the plates than outside of them. Outside the plates, in the wider expanse of the vacuum, there were no such constraints, allowing for a fuller spectrum of wavelengths. The difference in the number of allowed modes would create a tiny but measurable pressure pushing the plates together, a force that would exist solely because of the zero-point energy of the quantum vacuum. Casimir's insight was revolutionary because it provided a concrete way to demonstrate the reality of zero-point energy. He calculated the force to be incredibly small, detectable only over extremely short distances in the range of nanometers, mere billionths of a meter. Several years after Casimir's theoretical prediction, the effect was confirmed experimentally. In the late 1950s and 1960s, more sophisticated experiments were conducted to measure the tiny force between such plates. However, it wasn't until 1997 that Steve Lamoureux at the University of Washington made a highly precise measurement of the Casimir force, confirming Casimir's predictions to within 5% accuracy. The experiment involved placing a flat plate near a spherical one, minimizing the challenges of aligning two perfectly parallel surfaces. This precise measurement validated the existence of the force that Casimir had predicted, proving that zero-point energy was not just a mathematical artifact, but a genuine physical phenomenon. The idea that the vacuum itself is imbued with zero-point energy has far-reaching implications. In classical physics, empty space is precisely that empty. In the quantum view, however, even the most perfect vacuum is filled with fluctuating fields and the constant emergence and annihilation of virtual particles. Here is where the concept of zero-point energy becomes crucial in discussions about the origin of the universe. The realization that the vacuum is not an inert, empty stage, but rather a dynamic, energetic fabric opens up new possibilities for understanding how the universe could arise from nothing. Within this quantum cauldron, every now and then, fluctuations occur that are not just ripples in energy, but actual, albeit fleeting, creations of particles. These quantum fluctuations can give birth to pairs of particles and antiparticles, such as an electron and its mirror opposite, the positron, which momentarily appear before annihilating each other in a burst of energy, returning to the void from which they sprang. This is not a rare occurrence. It happens all the time, everywhere, within the fabric of space itself. If one could peer into this quantum world, they would see not a calm, featureless expanse, but something more akin to boiling foam. Here, space-time itself is a bubbling broth, a frenetic, frothing fabric, constantly shifting, bending, and twisting under the influence of countless quantum events. And within this foam, something truly remarkable could happen. Imagine a particularly intense fluctuation, one so powerful that instead of quickly dissipating, it becomes the seed of something far more substantial. For in the strange logic of quantum mechanics, even a vacuum fluctuation, if it is potent enough, could give rise to a new realm, a new domain where energy and matter could begin to coalesce. This is where the nothing of the quantum void transforms into the something of a nascent universe. It is as if the quantum vacuum, brimming with energy and potential, becomes the crucible from which the cosmos emerges. But how does this all happen? What could push a fleeting fluctuation into becoming the first tangible echo of existence? To understand this, we must delve even deeper into the nature of time itself. Before the universe existed, the concept of time had no meaning. Time, as we know it, is a property that emerges from the fabric of space itself. In this foamy, fluctuating quantum realm, there was no before or after, no linear sequence of events. But with the birth of a universe seeded from a quantum fluctuation, the first faint whispers of time began to stir. The tiniest unit of time, known as the Planck time, is thought to be around 10 to the point of minus 43 seconds after this initial creation event. This is the first measurable moment, the smallest conceivable slice of time, beyond which our current understanding of physics begins to lose its grip. At this infinitesimally brief instant, the universe would have been unimaginably small, hot, and dense, a singularity of both infinite energy and infinite possibility. It is here, in this realm governed by quantum uncertainty and unimaginable density, that time as we perceive it began to unfold. In the chaos of quantum instability, the rules of our universe, rules that would govern the forces of nature, the constants that define the cosmos, were forged. The quantum foam, with its frothing potential, was not just a sea of randomness, but a fertile ground for the birth of time itself. In this moment, what we now call the Big Bang occurred not as a massive explosion in space, but as an expansion of space itself from a singularity born from the very quantum vacuum that paradoxically appears to us as nothing at all. The Planck time is not just a boundary on our ability to measure the universe's beginnings. It is a veil, shrouding a period when reality as we know it did not yet exist in any recognizable form. It is in this nascent realm that the concept of a quantum trigger comes into play, a moment when a significant quantum fluctuation could spark the birth of an entire universe. This idea, proposed by the cosmologist Alexander Vilenkin, suggests that the universe may have emerged spontaneously from a quantum vacuum fluctuation, not unlike the fluctuations that we see manifesting as virtual particles in the fabric of space itself. Vilenkin's theory, known as quantum tunneling from nothing, posits that our universe could have been born in a manner similar to the quantum tunneling that allows particles to move through energy barriers that they should not be able to pass. All right, let's try to understand it through an example. Imagine you're playing with a rubber ball in your backyard. There's a wooden fence that separates your yard from the neighbor's yard. In classical physics, if you throw the ball at the fence, it will bounce back because it doesn't have enough energy to go through the fence. In the quantum world, things get weird. Picture the ball as a tiny particle, like an electron, and the fence as a potential energy barrier. Even if the electron doesn't have enough energy to climb over the barrier, like the ball wouldn't jump over the fence, there's a small probability that the electron can tunnel through the barrier and appear on the other side, as if it magically passed through the fence without going over it. This phenomenon is called quantum tunneling. It's as if the ball, despite hitting the fence, occasionally ends up in the neighbor's yard without any visible pathway, thanks to the quirks of quantum mechanics. Crazy, right? The quantum world is full of such mind-bending surprises. Just as an electron can suddenly appear on the other side of a potential barrier due to the peculiarities of quantum mechanics, so too could the universe have tunneled into existence from a state of absolute nothingness. Vilenkin's theory hinges on the principle that, in the quantum realm, all possibilities have a non-zero chance of occurring, no matter how unlikely they may seem. This is the essence of quantum mechanics, an unpredictability that defies classical intuition, where events that seem impossible in the macroscopic world are entirely within the realm of plausibility at the quantum level. In this view, the universe could appear from nothing, not because of a cause or a pre-existing condition, but because nothingness itself in quantum terms is not truly empty. It is a state brimming with potential, capable of giving rise to something, a quantum fluctuation of unimaginable scale that could result in the birth of a universe. But for this infant universe to evolve into the vast cosmos we see today, something dramatic had to happen, something that could take a minuscule quantum fluctuation and blow it up to cosmic proportions. This is where the role of symmetry breaking and inflation enters the story. The theory of cosmic inflation was initially proposed by Alan Guth in 1980. Guth, a theoretical physicist at the Massachusetts Institute of Technology, was grappling with some troubling inconsistencies in the standard Big Bang model, particularly the horizon and flatness problems. The horizon problem arises from the observation that regions of the universe, seemingly too far apart to have ever been in contact, share an almost uniform temperature. The flatness problem refers to the observation that the universe appears to be perfectly balanced between continuing expansion and gravitational collapse. These problems suggested that something significant had occurred in the early moments of the universe to make it appear so remarkably uniform and balanced. Guth's groundbreaking insight came from a seemingly unrelated field: particle physics. He realized that the early universe might have undergone a phase transition, much like water freezing into ice, which released a tremendous amount of energy and drove a rapid expansion of space, an inflationary burst. This inflation would have stretched the universe by an exponential factor in a tiny fraction of a second, effectively smoothing out any irregularities and creating the observed uniformity. While Guth's original model faced problems like ending inflation too abruptly, leading to what was known as the graceful exit problem, his concept ignited a flurry of research that quickly refined the idea of inflation and placed it at the heart of modern cosmology. Andrei Linde, a Russian physicist at Stanford University, extended Guth's work by proposing the new inflation and later chaotic inflation models, which offered solutions to the issues that plagued Guth's original theory. Linde's models suggested that inflation could occur in a much broader range of conditions and did not require as fine-tuned a starting point. Chaotic inflation, in particular, posited that inflation could arise spontaneously from random quantum fluctuations in a high-energy field, providing a natural mechanism for the birth of our universe from a state of nothing. The core idea was that in the earliest moments of existence, a high-energy field known as the inflaton field dominated the universe. As this field's energy decreased, it triggered a rapid, exponential expansion of space. Inflation was not just a stretching of pre-existing space, it was the very birth of space and time itself. In the pre-inflationary era, as modern theories suggest, the universe existed in a quantum state without the defined structure of space-time. It was a singularity, an infinitesimal point where density and temperature reached infinite values, and the classical concepts of space and time dissolved. According to Einstein's general relativity, this singularity marks a breakdown of our conventional understanding of physics. However, quantum mechanics introduces the possibility that even this singularity is not truly a beginning in the classical sense. Instead, it could represent a state of pure quantum potentiality, a foam of possibilities from which space and time might emerge. During the inflationary period, this quantum foam underwent a phase transition that led to the birth of space-time. The inflaton field, which pervaded this early state, is thought to have contained enormous amounts of potential energy. As the field decayed, this potential energy converted into kinetic energy, resulting in an enormous outburst of rapid expansion. This expansion smoothed out any initial quantum fluctuations, but crucially also stretched these fluctuations across the universe, seeding the distribution of matter that would eventually coalesce into galaxies, stars, and planets. In this way, inflation not only created the macroscopic structure of the universe, but also served as a bridge between the quantum and classical realms. Stephen Hawking, alongside James Hartle, further explored this concept by proposing the no-boundary hypothesis. This model, developed in the 1980s, suggested that the universe does not have a singular beginning, a boundary in time before which nothing existed. Instead, time itself becomes another dimension of space under extreme conditions, such as those at the very early moments of the universe. According to Hawking and Hartle, during inflation, the distinction between time and space becomes blurred, and time, as we know it, gradually emerges as a consequence of the universe's expansion. In their view, the universe could be self-contained and without a boundary, meaning it could have emerged from a state of pure potential without a defined starting point. The rapid inflation of the universe was essential for this birth of space-time because it effectively separated time from the quantum gravitational fog of the singularity. Before inflation, time did not flow in any conventional sense because there was no space for it to move through. As inflation unfolded, however, it created a defined space-time fabric, stretching the quantum fluctuations of the vacuum and laying down the framework upon which time could unfold. This is a profound idea that time, as we experience it, may have been born from a quantum field's decay, a spontaneous event that triggered not only the creation of vast stretches of space, but also the forward arrow of time itself. As the inflaton field decayed, it gave rise to an enormous amount of energy, which rapidly cooled and transformed into the elementary particles that would form the universe. The transition from quantum to classical descriptions of reality, from uncertainty to the certainty of existence, can thus be seen as a natural outcome of the inflationary process. In this context, the birth of the universe from nothing is not a mere philosophical notion, but a prediction of the laws governing the quantum world. As quantum mechanics tells us, particles can spontaneously appear and disappear, tunneling in and out of existence. Inflationary theory extends this idea to space-time itself, suggesting that the universe was born from a fluctuation of a quantum field, expanding exponentially and giving rise to the space and time we inhabit. These ideas are not just abstract theoretical constructs, they have also found empirical support. Observations of the cosmic microwave background, the afterglow of the Big Bang, provide a snapshot of the universe as it existed just 380,000 years after its inception. The slight temperature variations in the CMB are thought to be the imprints of quantum fluctuations stretched across the cosmos during inflation. Experiments such as those conducted by the Planck satellite have mapped these variations with exquisite precision, confirming the predictions of inflationary theory and giving us a direct glimpse into the earliest moments of the universe's birth. Thus, from a quantum inflationary perspective, the birth of space and time can be seen as a transition from a state of infinite quantum possibilities to a structured, expanding universe. Inflation created the conditions necessary for spacetime to emerge from a singularity, knitting together the laws of quantum mechanics with those of general relativity. This not only makes the universe's creation from nothing conceivable, but also hints at the profound connections between the smallest quantum scales and the grandest cosmological structures. The universe, as we understand it, is a manifestation of quantum fluctuations writ large, a cosmic tapestry woven from the fabric of quantum fields, stretched and shaped by the inflationary burst that marked the beginning of everything we know. If inflation can give rise to a universe from a quantum fluctuation, it might also mean that countless other universes are out there, each birthed from its own quantum seed in the infinite expanse of the quantum field. Could it be that our cosmos is just one of an infinite tapestry, each universe expanding and evolving with its own unique laws, its unique constants, and its own fate? In the strange world of quantum mechanics, where particles can exist in multiple states at once and where reality seems to blur at the edges, the notion that the cosmos we inhabit might be but one of countless others suddenly becomes not just plausible, but inevitable. This is the starting point of the multiverse hypothesis, an idea that extends the implications of quantum theory to their furthest logical reach. If our universe began as a quantum fluctuation in a seething vacuum, then what's to stop countless other fluctuations from birthing their own universes, each with its own unique properties, its own dimensions of space and time, its own beginning, and perhaps its own end? To understand this, we must first dive into the concept of eternal inflation, proposed by Andre Linde in 1981. We've already explored how Alan Guth's original theory of inflation gave a solution to the universe's early mysteries, like its smoothness and uniformity, by suggesting a rapid exponential expansion of space immediately after the Big Bang. Andre Linde, however, took this concept much further, leading us into even more profound territory. His theory of eternal inflation does more than just solve the cosmological puzzles left by Guth. It opens the door to a potentially infinite multiverse, where countless universes are born from the fundamental principles of quantum mechanics. Linde's idea begins with a deeper look at inflation itself. In Guth's model, inflation was a one-time event, a brief moment when the inflaton field, a scalar field believed to have driven the rapid expansion, pushed the universe outward, smoothing it and setting the stage for all future cosmic evolution. But Linde saw inflation not as a singular event, but as a continuous, eternal process. The key to his theory lies in the nature of quantum fields and the fundamental randomness of quantum mechanics. In quantum field theory, every field, including the inflaton field, is subject to quantum fluctuations, tiny random changes that occur even in what appears to be empty space. These fluctuations cause the inflaton field to vary randomly across different regions. In some places, the field's value might drop, allowing inflation to stop and a universe like ours to form, with normal space and time beginning to unfold. But in other regions, the value of the field remains high, and inflation continues, causing those regions to expand exponentially faster than the speed of light. This ongoing inflation creates a dynamic scenario where some regions slow down to become universes, while others keep inflating indefinitely. Linda's theory, therefore, transforms our understanding of the cosmos from a single, isolated universe into an infinite multiverse, a collection of pocket universes, each forming in its own bubble from a vast, eternally inflating background. This process is akin to a never-ending chain reaction. Within the inflating space, some regions become islands, where inflation stops and a universe like ours forms, while elsewhere, inflation persists, creating more and more universes. The notion that different bubble universes might be entangled raises even deeper questions about the nature of reality. Julian Barber, a physicist who has spent much of his career contemplating the nature of time, offers a fascinating perspective that dovetails with the concept of an entangled multiverse. Barber challenges the traditional view of time as a continuous, flowing river. Instead, he proposes that time is composed of a series of discrete nows, or moments, each one separate and distinct from the others. In his timeless model of reality, past and future are merely illusions created by our perception. Only the present moment truly exists. Barber's ideas resonate with the quantum world, where particles do not have definite properties until they are observed. In quantum mechanics, the act of measurement forces a particle to choose a particular state, collapsing its wave function and making its position or velocity definite. Similarly, Barber suggests that each now is like a snapshot of the universe, a single quantum state that exists independently of all others. If we extend this idea to the multiverse, could each now correspond to a different bubble universe? Each moment, a separate thread in the vast tapestry of existence, connected to others by the hidden threads of quantum entanglement? This possibility finds an echo in the work of physicists who have proposed that time itself might be an emergent phenomenon, a byproduct of quantum entanglement. Carlo Rovelli, a leading figure in the field of quantum gravity, has argued that time as we perceive it is not fundamental, but emerges from the way quantum systems interact with one another. In Rovelli's relational interpretation of quantum mechanics, time does not exist as an absolute external entity. It is defined by the changing relationships between different quantum systems. In a multiverse context, this suggests that time might vary from one universe to another, depending on the unique configuration of quantum fields and particles within each bubble. If time is indeed emergent, and if the multiverse is a vast collection of entangled quantum states, then our understanding of reality becomes even more fluid and interconnected. The fates of different universes might influence one another through the subtle threads of quantum entanglement, rippling through the fabric of space-time like echoes in an infinite cosmic cave. Could the laws of physics themselves be different in each universe, shaped by the specific quantum entanglements that brought them into being? And if so, could there be a way to detect or even communicate across these vast distances using the strange non-local properties of entanglement? These questions remain speculative, but are grounded in the cutting-edge theories of physicists who are pushing the boundaries of our understanding. As we continue to explore the quantum frontier, we may discover that the universe, or rather the multiverse, is far more interconnected and mysterious than we ever imagined, a grand tapestry woven from the quantum threads of reality itself. If the quantum multiverse hints at an infinite cosmic landscape, where universes are born like sparks from a cosmic fire, it forces us to confront an even more profound mystery. What ignites these sparks? What drives these bursts of creation from the depths of nothingness? To answer this, we must plunge deeper into the very fabric of existence, into the strange, shadowy world of particle physics, where reality itself is woven from the most fundamental threads. As discussed in previous chapters, the concept of multiple universes challenges our understanding of reality. Yet, to truly grasp how such a mind-boggling idea can even be considered, we need to step back into the smallest scale possible, the world of particles, forces, and fields. Similarly, in quantum cosmology, the birth of the universe is often described in terms of probabilities, with different outcomes, different universes arising from various quantum states. This approach hinges on the foundations laid by particle physics, which deals with the smallest building blocks of nature and how they interact. One of the most significant players in the early moments of the universe's formation was the Higgs field, a mysterious but crucial ingredient that allowed the cosmos to take shape as we know it today. Imagine the universe in its infancy, mere moments after the Big Bang, an incredibly hot, dense environment filled with energy. In this early state, particles were massless, zipping around at the speed of light, unable to coalesce into the matter that would later form stars, planets, and life itself. The Higgs field changed all of that. It is a vast, all-pervading energy field, filling every corner of the universe and providing particles with mass. Without it, nothing in the universe would have any weight, and matter as we know it could not exist. To understand why the Higgs field is so essential, let's first grasp what it does. The Higgs field is often compared to molasses or a thick syrup, a medium that particles must push through as they travel. As a particle moves through this field, it interacts with it, and in doing so, it gains mass. The more the particle interacts with the field, the more massive it becomes. The field doesn't affect all particles equally. Some particles, like photons, which are particles of light, don't interact with the Higgs field at all and remain massless. Other particles, like quarks and electrons, interact more strongly with the Higgs field and thus gain mass. A useful analogy to visualize this process is imagining walking through a crowded room. If the room is empty, you can move freely and quickly, much like a massless particle. But as the room fills with people, it becomes harder to move. Every step you take is slowed down by the crowd around you. This resistance is similar to how the Higgs field interacts with particles. The more crowded the room, the more you have to push through. And in the universe's case, this crowd is the Higgs field slowing down particles, giving them mass. Without the Higgs field acting like this cosmic molasses, particles would continue zipping around massless, never clumping together to form atoms, molecules, or the universe as we know it. This process, however, isn't something that was immediately obvious. In fact, the existence of the Higgs field was one of the biggest mysteries in physics, until it was confirmed in 2012 with the discovery of the Higgs boson. The Higgs boson is the particle associated with the Higgs field, and its discovery was a monumental achievement, verifying a key part of the standard model of particle physics, the theoretical framework that explains how the basic building blocks of the universe interact. To appreciate the importance of the Higgs field, we must place it within the broader context of the standard model. Developed over decades by some of the brightest minds in physics, including Sheldon Glashow, Abdus Salam, and Steven Weinberg. The standard model represents a culmination of efforts to understand the tiniest pieces of reality. It describes all known fundamental particles, such as quarks, which make up protons and neutrons, leptons, like the electron, and bosons, particles that mediate forces such as photons and gluons. These particles don't just exist in isolation, they interact with each other through four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each of these forces governs a different aspect of the universe, from holding atomic nuclei together to enabling the formation of electromagnetic radiation, like light. The Standard Model has been remarkably successful at explaining three of these four forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Electromagnetism, the force responsible for light, electricity, and magnetism, is well understood thanks to quantum electrodynamics. The weak nuclear force, which governs radioactive decay, and the strong nuclear force, which holds atomic nuclei together, are also explained within the Standard Model. However, one of the most challenging aspects of unifying our understanding of the universe lies in the fourth force: gravity. Gravity, the force that governs the movement of planets, stars, and galaxies, and which gives weight to objects here on Earth, is conspicuously absent from the Standard Model. The Standard Model explains the quantum world, the realm of the very small, while gravity is described by Einstein's general theory of relativity, which deals with the large-scale structure of the universe. Reconciling these two theories into a single framework, a theory of everything, has been one of the holy grails of physics. This is one reason the Higgs field is so exciting. It's a step toward understanding how particles gain mass, and it hints at deeper connections between the quantum world and the larger cosmos. The discovery of the Higgs boson was the key to proving the existence of the Higgs field. However, detecting the Higgs boson was no simple task. To find it, scientists needed to recreate conditions similar to those of the early universe, conditions with extremely high energies. This is where the Large Hadron Collider comes into play. The LHC, located at CERN in Geneva, Switzerland, is the largest and most powerful particle accelerator in the world. It accelerates protons to nearly the speed of light and then smashes them together, creating a tiny burst of energy. For just a fraction of a second, this energy can recreate the extreme conditions of the early universe, allowing scientists to glimpse particles that normally wouldn't exist in everyday life. In 2012, after years of running these high-energy collisions, researchers at CERN announced that they had detected a new particle, the Higgs boson. The discovery was hailed as one of the greatest scientific achievements of the 21st century. It confirmed that the Higgs field existed, providing the missing piece in our understanding of how particles gain mass and validating decades of theoretical work. The discovery of the Higgs boson and the confirmation of the Higgs field was a monumental step in our understanding of the universe, but it was far from the final chapter. In fact, it was more like a stepping stone, leading us toward even more ambitious theories that aim to explain the entire fabric of reality. After all, while the Higgs field explains how particles gain mass, it doesn't explain everything. One of the biggest mysteries it leaves unresolved is the fundamental force of gravity, the very thing that holds the universe together on a grand scale. This is where physicists turn to two major theoretical frameworks: grand unified theories, and string theory, both of which attempt to address the shortcomings of the Standard Model and bring us closer to a theory of everything. To begin, we must understand the historical roots of grand unified theories. The idea of unifying the fundamental forces of nature has been around since the late 19th century, when James Clerk Maxwell successfully unified electricity and magnetism into a single theory known as electromagnetism. This breakthrough set a precedent for the idea that the forces governing the universe could in fact be connected, different manifestations of the same underlying reality. Fast forward to the 20th century, when physicists such as Sheldon Glashow developed a theory that successfully unified two of the remaining forces, electromagnetism and the weak nuclear force. This theory, known as the electroweak theory, showed that at extremely high energies, like those present in the early universe, the electromagnetic force and the weak force merge into a single, unified force. This was a huge step forward and became a cornerstone of the Standard Model, but the ultimate goal of unifying all forces still lay beyond the horizon. That's where grand unified theories come in. Grand unified theories aim to take the unification process one step further by bringing together the electroweak force and the strong nuclear force, which holds the nuclei of atoms together. According to grand unified theory, all three of these forces, electromagnetism, the weak nuclear force, and the strong nuclear force, were once a single, unified force in the extremely high-energy environment of the early universe. Only as the universe expanded and cooled did these forces break apart into the distinct forces we observe today. In grand unified theory, physicists use complex equations to describe how a high-energy symmetrical state can give rise to the less symmetrical, lower-energy states we observe today. One of the major predictions of grand unified theory is that at incredibly high energies, far beyond what we can achieve with current particle accelerators, the strong, weak, and electromagnetic forces would behave as a single force. This means that if we could build a particle accelerator powerful enough to recreate the conditions of the early universe, we might be able to observe this unification firsthand. However, grand unified theory remains speculative because we currently lack the technology to test them directly. The energies required to observe the unification of the strong, weak, and electromagnetic forces are orders of magnitude higher than those we can generate with the Large Hadron Collider. Moreover, grand unified theory makes some bold predictions that have yet to be confirmed. For example, many predict that protons, the building blocks of atomic nuclei, should eventually decay over incredibly long time scales. If proton decay were observed, it would be a strong indication that we are on the right track. However, despite decades of searching, no definitive evidence of proton decay has been found, leaving grand unified theory in the realm of promising but unproven theories. While grand unified theories focused on unifying the three quantum forces of the Standard Model, they still don't solve the problem of gravity. This is where the next great leap in theoretical physics comes into play: string theory. If grand unified theories aim to unify the three quantum forces, string theory goes even further, attempting to include gravity in the unification process. The problem with gravity, as mentioned earlier, is that it doesn't fit into the Standard Model. The reason for this lies in the fundamental difference between how gravity and the other forces are described. The Standard Model relies on quantum mechanics, which deals with particles and their interactions at incredibly small scales. Gravity, on the other hand, is described by general relativity, Einstein's theory of space-time and gravity, which works beautifully on large scales, like planets, stars, and galaxies, but breaks down when applied to the quantum level. This incompatibility between quantum mechanics and general relativity has been one of the greatest puzzles in modern physics. String theory offers a possible solution by proposing a radical idea. What if, instead of thinking of particles as tiny points, we imagine them as tiny vibrating strings? In string theory, all fundamental particles, quarks, electrons, photons, and even the Higgs boson, are actually different vibrations of tiny strings. These strings are incredibly small, far smaller than anything we could ever observe directly, but their vibrations determine the properties of the particles we see. For example, one type of vibration might correspond to an electron, while another vibration could represent a quark. The beauty of string theory is that it naturally incorporates gravity. In string theory, one particular vibration of the string corresponds to a particle known as the graviton, which mediates the force of gravity. This means that string theory unifies not just the quantum forces of the Standard Model, but also gravity, offering the tantalizing possibility of a theory of everything, a single framework that describes all the forces and particles in the universe. One of the challenges with string theory, like grand unified theory, is that it's incredibly difficult to test experimentally. The strings in string theory are so small, on the order of the Planck length, which is 10 to the minus 35 meters, that no current or foreseeable technology can directly observe them. This has led some critics to argue that string theory is more of a mathematical framework than a physical theory, as it hasn't yet made testable predictions that can be experimentally verified. Despite this, string theory remains one of the most popular and extensively studied approaches to unifying gravity with the other forces of nature. By this point, you might be scratching your head, wondering what this is all about. So let's step back for a moment, recap what we've explained earlier, and connect it to what we're discussing here. As we weave these intricate theories together, grand unified theories, string theory, and the Standard Model, a fascinating picture begins to emerge. A universe that not only operates under complex, elegant laws, but one that might have arisen from nothing. To grasp how this is possible, we must begin with a fundamental concept in quantum physics: quantum fluctuations. Remember that according to quantum theory, even what we think of as empty space is not truly empty. In the quantum realm, nothing is ever completely still or devoid of activity. Instead, the vacuum of space teems with temporary particles popping in and out of existence due to fluctuations in energy. This quantum foam, as it's sometimes called, means that on the smallest scales, particles and fields can momentarily appear from nowhere, only to disappear again just as quickly. It's precisely this idea, particles springing into existence from nothing, that forms the bedrock of the quantum theory of the universe's birth. In the quantum world, fluctuations can give rise to something out of nothing. But how could this lead to the birth of an entire universe? Here's where modern physics offers a startling possibility. The same quantum processes that give rise to fleeting particles in a vacuum could, under the right conditions, give rise to a universe. One of the key ideas is that the total energy of the universe could actually be zero. This may sound counterintuitive at first. How could a universe filled with matter, stars, galaxies, and forces have zero energy? The answer lies in the balance between different types of energy. On one side, we have the positive energy contained in matter and radiation. On the other side, we have the negative energy associated with gravity. Gravity, unlike other forces, pulls things together, creating a kind of negative energy. When you add up all the positive energy of matter and all the negative energy of gravity, it's possible that the total energy of the universe is exactly zero. If the universe has zero total energy, then quantum mechanics suggests that it could have emerged spontaneously from nothing, just as virtual particles do in a vacuum. This idea gains more support from the framework of grand unified theories and string theory, which attempt to describe the universe at incredibly high energies similar to those that would have been present in the earliest moments after the Big Bang. In grand unified theory, as we discussed, all forces were once unified in the ultra-high energy environment of the early universe. This state of unification could have been triggered by a quantum fluctuation within the vacuum itself, sparking the rapid expansion we know as the Big Bang. Before this fluctuation, there would have been no matter, no energy, no space, and no time, just a quantum vacuum, a realm governed by the strange rules of quantum mechanics. As speculative as these ideas might seem, they are rooted in the same quantum principles that have been experimentally confirmed in laboratories for decades. Quantum fluctuations, the interplay of symmetry breaking in grand unified theories, and the potential for extra dimensions in string theory all provide a consistent framework for understanding how a universe, our universe, could have been born from nothing. The key is that nothing in quantum physics isn't truly nothing. It's a state of potential, a place where energy, fields, and forces are all poised to come into existence at any moment. And under the right conditions, such as those described by grand unified theory or string theory, the potential can give rise to an entire universe. But what about the inflationary theory of the universe, which describes the rapid expansion that followed the Big Bang? Inflation fits perfectly with the idea of the universe emerging from nothing because it explains how an initial tiny fluctuation, a quantum blip in the vacuum, could have inflated into the vast universe we see today. Inflation posits that in the earliest fractions of a second, the universe expanded exponentially, smoothing out any irregularities and laying the foundation for the galaxies, stars, and planets that would eventually form. Inflation provides a mechanism for how a universe born from a quantum fluctuation could grow large and stable enough to form the cosmos. In this view, the birth of the universe wasn't a one-off event, but part of the natural behavior of quantum fields. From nothing, a quantum fluctuation can trigger the birth of a universe. Inflation then rapidly expands that universe, and as it cools, symmetry breaks, giving rise to the distinct forces and particles we observe today. Grand unified theories describe how the unified forces of the early universe split apart, while string theory offers a broader perspective, suggesting that our universe could be one of many, born from fluctuations in higher dimensions. As we stand on the edge of these profound ideas, the birth of the universe from nothing invites even more tantalizing questions. If quantum mechanics, grand unified theories, and string theory offer a glimpse into how our universe began, what do they tell us about its ultimate fate? Could the same quantum forces that sparked the universe's creation also govern its future, and perhaps even its end? As we reach the end of our exploration, we find ourselves circling back to the central enigma, the paradox of something arising from nothing. The very notion defies our everyday experience, and yet, in the realm of quantum mechanics, such paradoxes are woven into the fabric of reality. Quantum theory tells us that even in the absence of particles and matter, the vacuum is not truly empty. It is a dynamic, restless state filled with potential and governed by rules that defy classical logic. If the quantum vacuum is filled with fleeting particles, virtual energies, and fluctuations that can give rise to entire universes, we are forced to ask, was there ever truly nothing? Or does the nature of quantum laws make existence in some form inevitable? This question is more than a philosophical musing. It strikes at the core of our understanding of the cosmos. Quantum mechanics has already shown us that reality is far stranger than we could have ever imagined. It challenges the very foundations upon which our concepts of time, space, and matter are built. In the quantum realm, particles can be in multiple places at once, exist and not exist simultaneously, and become entangled across vast distances in a way that defies conventional understanding. This defiance extends to our notion of nothingness, which, in quantum mechanics, seems to be just another state, a backdrop against which existence and non-existence play out their dance. But if existence is indeed a fundamental consequence of the quantum laws, then perhaps nothing is not a true state of reality, but a transitional phase, a canvas upon which the cosmos can emerge. The quantum fluctuations that seeded our universe may not be exceptions but the rule, hinting that the emergence of universes might be an intrinsic feature of reality itself. In this sense, the birth of the universe from nothing may not have been an improbable event, but rather an inevitable consequence of the quantum conditions that exist beneath the surface of all things. Yet even as we consider these possibilities, we are left with a profound mystery. If quantum mechanics suggests that nothing is never truly nothing, are we any closer to understanding why there is something at all? Is the universe a random fluctuation, a cosmic accident, or does it hint at a deeper, more fundamental structure? Does the quantum world hold the keys to the ultimate question of existence, or is it merely another step in an endless journey toward understanding? These reflections lead us to confront the limits of our knowledge. Quantum mechanics, for all its success in describing the minutiae of particle interactions and cosmic phenomena, still presents us with puzzles that defy easy explanation. Time may not flow as we perceive it, space may not be as solid as it seems. At every turn, quantum mechanics forces us to reconsider our assumptions, to embrace the uncertainty and paradox that lie at the heart of reality. So we are left with the final tantalizing question: is there ever truly nothing, or is existence itself woven into the fabric of the quantum universe? What caused this explosion in the first place is still a mystery. As we stand on the brink of these profound mysteries, we recognize that our journey has only just begun. The universe, born from a quantum fluctuation, may be but one chapter in an infinite story, a testament to the power and mystery of the quantum laws that govern all that is. And perhaps, somewhere in the interplay between nothingness and existence lies the answer to the oldest question of all. Why is there something rather than nothing?